In the Wurzburg laboratory of experimental physicists Professor Matthias Bode and Dr. Artemodo Besco, groundbreaking work in quantum research is taking place, driven by the extreme conditions they create. Affiliated with the Cluster of Excellence CD, QMAT, a collaboration between JMU Wurzburg and TU Dresden. Their latest achievement involves unveiling the Spinaron effect. This scientific endeavor involves a combination of precise techniques and equipment, including the strategic placement of individual cobalt atoms onto a copper surface, chilling them to an incredibly low temperature of 1.4 Kelvin, minus 271.75 degrees Celsius, and subjecting them to a powerful external magnetic field. Professor Bode emphasizes the high cost of the specialized magnet used in this process, highlighting the unique and exclusive nature of their experimental setup. At the heart of their work is the study of individual cobalt atoms, which exhibit a property called spin, akin to magnetic north or south poles. The ability to measure these spins is essential for their groundbreaking discoveries. Please subscribe to our channel so that we can bring more content to your favorite quantum world. The scientists employed a scanning tunneling microscope to observe and manipulate these tiny atoms. Their research focuses on understanding correlation effects within quantum materials, aligning with the mission of CD, QMAT, which aims to drive technological innovations through quantum research. Traditionally, since the 1960s, solid-state physicists have relied on the Kondo effect to explain the interaction between cobalt and copper. This effect involves the cancellation of magnetic orientations, resulting in the formation of a Kondo cloud where copper electrons are bound to cobalt atoms. However, Professor Bode and his team ventured beyond this conventional understanding. They validated an alternate theory proposed in 2020 by theorist Samir Launis from the Forschungszentrum Jülich. The breakthrough came by harnessing the power of an intense external magnetic field and employing an iron tip within the scanning tunneling microscope. This allowed the researchers to determine the magnetic orientation of cobalt spin. Intriguingly, the cobalt atom's spin isn't fixed. It continuously switches between spin-up and spin-down states, exciting the surrounding copper electrons. This phenomenon, termed the Spinaron effect, was previously predicted by Samir Launis. Professor Bode offers an analogy, likening the cobalt atom state to a spinning rugby ball, causing surrounding elements to oscillate, ultimately leading to a bond between copper electrons and the cobalt atom. This experimental validation of the Spinaron effect challenges the long-held belief in the universal applicability of the Kondo effect to explain interactions between magnetic atoms and electrons in quantum materials like cobalt and copper. Professor Bode humorously suggests that physics textbooks may need a significant asterisk. The Spinaron effect has significant implications for understanding magnetic moments on metal surfaces. Looking ahead, this phenomenon could open doors to advancements in magnetic information, encoding, and transportation, a field known as spintronics. This innovation could potentially lead to more energy-efficient and environmentally friendly information technology solutions. However, Professor Bode cautions against overly optimistic expectations regarding the practical application of the cobalt-copper combination. The precise conditions required for their experiments, involving individual atoms at ultra-low temperatures in ultra-high vacuum environments, are far from feasible for everyday devices like cell phones. Nonetheless, their work represents a milestone in fundamental research, shedding light on the behavior of matter at the quantum level and paving the way for potential future applications. Currently, quantum physicist Artemodo Besco and theorist Samir Launis are engaged in a comprehensive review of numerous publications dating back to the 1960s that describe the Kondo effect in various material combinations. They suspect that many of these publications might actually be describing the Spinaron effect, which could lead to a significant revision of the history of theoretical quantum physics.